Bismillahirrahmanirrahim. Welcome to the course of Electric Machine 2, lecture number 10. Today we are going to study how synchronous motor start. In our last lecture we have studied the basic of synchronous motor and its working principle. So let's start. First method is with external prime mover. We can use an external prime mover to start a synchronous motor. So how it works? That is, synchronous motor are coupled mechanically with another motor, three-phase induction motor or DC shunt motor. Initially we do not apply DC excitation to rotor. When it rotates at a speed very close to synchronous speed, then the DC excitation is given, and when magnetic locking takes place, external motor supply is cut off. So in this method we use a three-phase induction motor or DC shunt motor. Initially we not apply excitation to rotor, and when the rotor reach the speed nearly to synchronous speed, then the DC excitation is given. The second method is with damper winding. In order to make the motor self-starting, a squirrel gauge winding, also called a damper winding, is provided on the rotor. The damper winding consists of copper bar fixed in the pole face of the rotor. The bar are short-circuited at the end to form squirrel gauge. A three-phase supply is given to the stator winding while the rotor field is left unenergized. The rotating stator field induces current in damper or squirrel gauge winding, and the motor starts as an induction motor. When motor approaches the synchronous speed, the rotor is excited with DC. As a result, a strong magnetic attraction is set up between stator poles and rotor. The rotor poles lock in with the poles of rotating flux, that is the stator rotating magnetic field. Consequently, the rotor revolves at the same speed as the stator field, that is at a synchronous speed. So in this method we use a squirrel gauge winding, and it is the copper bar fixed on the pole face of the rotor. The bars are short-circuited at the end to form a squirrel gauge, and then initially we supply a three-phase to the stator winding, which produce a rotating magnetic field, and the rotor is unenergized, mean the voltage induced. The rotating magnetic field cut the rotor bars and EMF induced in it, and in this way, due to short circuited, the current flow in it, and due to the rotating nature of the field, the rotor start to rotate, and when it reach the synchronous speed, the rotor is excited then, and due to the magnetic locking take place, the rotor revolves at the same speed as the stator speed. So this is the method called damper winding method. Now there are different excitation. We can excite differently to get different condition with the power factors. So synchronous motor, different excitations. So when synchronous motor is excited in such manner that back EMF is equal to the supply voltage, We call it normally excited. When it is under excited, the field excitation is such that back EMF is less than the supply voltage, and when the back EMF is greater than the supply voltage, the motor is said to be overexcited. In both normal and under excitation, the motor has lagging power factor. However, for our excitation, the motor has leading power factors. So when we can excite the motor differently, we get different condition and we get different power factor. That is one of the characteristics of the synchronous motor, that it operates for different power factor, lagging, leading. Now what happens when we connect load to synchronous motor? We know that a synchronous motor run at a synchronous speed at all loads. It meets the increased load not by decrease in speed but by relative shift between stator and rotor poles, that is by adjusting of a torque angle. So the angular displacement between stator and rotor pole called torque angle. If the load on the motor increased, the torque angle also increased, that is the rotor pole lagged behind the stator pole by a greater angle. But the motor continued to run at a synchronous speed. When we connect load to synchronous motor, and if the load increase or decrease, the speed remain constant as it is a synchronous motor, so no change in speed. The only change that happen is that the torque angle increase or decrease with load. Now, what is a torque angle? The angle between stator and rotor poles, and it is denoted from alpha. So when the load increase, the torque angle also increase. Rotor poles lag behind the stator poles by a greater angle, and the motor continue to run at a synchronous speed. The increase in torque angle causes a greater phase shift of back EMF EB with respect to the supply voltage V. When the angle increase, a great phase shift of back EMF with respect to the supply voltage. This increase the net voltage ER, resultant voltage in a stator winding. Consequently, armature current IA, which is equal to the difference between V minus AB, is equal to ER by impedance, increase to meet the load demand. So this is another very important point, that when a torque angle alpha cause a greater phase shift, that is when the load increase, the torque angle also increase, and there is a shift of EMF, back EMF with respect to the supply voltage, and this increase the net voltage ER in the stator winding. Consequently, armature current increases to meet the load demand. Now if the load on the motor decreases, the torque angle alpha also decreases. This causes a smaller phase shift of the back EMF with respect to voltage. Consequently, the net voltage or the resultant voltage in a stator winding decreases, and also the armature current decreases. So we studied motor on load, and we know about the synchronous motor, that increase in load or decrease in load, the speed remain constant, but there is a phase shift EB with respect to the supply voltage. In this way, the resultant voltage increase or decrease, and with this increase or decrease of the resultant voltage, the current in armature also increase or decrease to meet the load demand. Now this is the under excitation, how the motor behave in under excitation. Under excitation mean when the supply voltage is greater than the back EMF. So the motor is said to be under excited if the field excitation is such that V is greater than EB. Under such a condition, the current IA, armature current, lag behind voltage, so that motor power factor is lagging. Since voltage is greater than back EMF, the net voltage, resultant voltage, is decreased and turned clockwise as angle between resultant voltage and current is constant, that is 90. Therefore, phasor armature current also turns clockwise. Current IA lags behind the supply voltage. Consequently, the motor has lagging power factors. Another condition, that is the normal excitation. When the supply voltage is equal to the back EMF, the motor is said to be normally excited. If the field excitation is such, note that the effect of increasing excitation, that is increasing the back EMF, is to turn the phasor ER and hence IA in anti-clockwise direction, that is IA phasor has come closer to the phasor V, therefore power factor increase though still lagging. As we already studied that increasing of load or decreasing of load only shift EB with respect to V, and the resultant EMF directly affect the armature current. So this is the shift of EB with respect to V, and in this way the power factor is improved. Now the hour excitation. The motor is said to be hour excited if the field excitation is such that the back EMF is greater than the supply voltage. Under such a condition, current in the armature leads the voltage and the motor power factor is leading. Note that the resultant voltage and hence IA further turn in anti-clockwise direction form the normal excitation position. Consequently, IA lead the voltage. These are the different conditions, that is under excitation, normal excitation, unity power factor, and our excitation system. As we see, this is the voltage and that is the back EMF. This is the armature current and this is the resultant EMF, which is the aiding when we resolving the components voltage and back EMF, we got the ER. So when increase in load or decrease in load happen, this back EMF shift with respect to the voltage, it increase or decrease, it mean its angle become more or less. In this way, this ER shift like is shown in this, and again see in this, and in the over excitation it is shifting from voltage in the anti-clockwise direction. In similar manner, when the back EMF shift, the resultant EMF also shift or increase or decrease, in which affect the armature current, and in our excitation it lead the voltage in the rest of the normal excitation and under excitation it's lag. So in under excitation and normal excitation the power factor is lagging, in our excitation it is leading. So this is the advantage or the application of the synchronous motor, that we can use it for power factor improvement. Now application of synchronous motor. Synchronous motor having no load connected to its shaft is used for power factor improvement, owing to its characteristic to behave at any electrical power factor. It is used in power system in situation where static capacitors are expensive. The next one is when operating speed is less and high power is required, that is when 35 kilowatt to 2500 kilowatt. The size, weight and cost of the corresponding three-phase induction motor is very high. Hence these motors are perfectly used, that is in pump, compressor, reciprocating, rolling miles, etc. So this is the today lecture.